Hello everyone, welcome back to ptet.chemistry channel. So my name is Mr. On. So in this tutorial video, I'll go through what is supposed to be a topical test on stats of matter. This is under the new 2023 syllabus for the Cambridge International exams. Regardless, I suppose most of the syllabus content would have overlap with what was previously known as just kinetic particle theory. So it's a bit of rebranding, but most of the concepts covered are kind of similar anyway. All right. So when I set this paper, I had a mixture of MCQ as well as structured questions. And for 44 marks, I set it to be 15 minutes. But give and take, I suppose you could probably take up to an hour maximum because the longer time you need to complete the paper means that you are not training yourself under exam condition. Okay, so I'll try and finish this in maybe an hour because I'll be going through concepts and I'll be going through things in a little bit detail from time to time, different questions, because there's a goal of this kind of tutorial video. Yeah, so feel free to use the chapter marker to skip to whichever questions that you're interested in. So in this first question, this is a multiple choice question. So which statement is not correct? So they even bolded it for you. So which statement is not correct means which statement is wrong. So we are looking for an incorrect statement, okay? So we have energy is released when a liquid changes into a solid. So we say energy is released. We know that when a solid goes to liquid, that is melting, and melting requires energy. Melting requires heat energy to be absorbed, which means when you go the other way, liquid going to solid, freezing will release energy because energy is simply converted from one form to another. So going from liquid to solid will release heat energy, and therefore A is a correct statement. So A is a correct statement, which means A is not what you want. Be very careful here. Particles move faster in the gaseous state than liquid state because gaseous state has more kinetic energy, okay? And you get gaseous state at a higher temperature than compared to the liquid anyway, all right? Carbon atoms in gaseous methane are further apart, all right? So it doesn't matter whether it is methane or diamond, but you can think of them as being gaseous. So the key term here really is gaseous versus solid. So gas versus solid, doesn't matter what the materials are. Essentially, when you have gas, the atoms, the particles, the molecules would be further apart compared to when they are solid. So this is again a correct statement, meaning to say if A, B, C are correct statement, D must be the incorrect statement. Let's go through it and convince ourselves. Yeah, there's a large decrease in the volume of a solid metal when pressure is applied to it. That is wrong. Solids cannot be compressed. So we talk about compressibility in terms of the spacing in between the particles. And when you have a solid, you have your particles very closely packed together and they're touching each other. So there isn't much more room for you to actually compress them. So solid cannot be compressed. Gas, on the other hand, can be compressed very, very well when you apply pressure to it, and your volume would decrease immensely, would decrease by a large amount. That should have been for a gas, not for a solid. For a gas, that is correct. All right. Question 2, a gas cylinder is placed in each of the 4 corners of a square room. So it's a gas cylinder, so it releases gas. Each gas contains a different gas stored under the same pressure. So under the same pressure, the gases are released at exactly the same time. Which gas will reach the center of the room first? So this is a question regarding diffusion. So at the moment in a topical kind of setting, it's very easy to see that it has got to be diffusion. But when it's in an actual paper, so a lot of students might get confused and they don't really relate to ideas of diffusion at all from their from learning all this kinetic particle theory. We talk about rate of diffusion depends on the molecular mass. So the heavier you are, the less far you will travel. Meaning to say, the lighter you are, the lower is your mass, the further you will travel, and therefore you will travel to the center of the room first. Okay. The other one is to do with temperature, but we are not dealing with temperature here. We are mainly dealing with the molecular masses. So to work out the molecular mass, you need your periodic table. Your periodic table shows you, I know the periodic table for all levels specifically shows you like 7 and 14 like that. This number at the bottom is shown in your periodic table. It said that this number at the bottom is called relative atomic mass. That's because there's the mass number. So use that. You have n, and if there's no number at the bottom, it means there's one of it. So there's just one nitrogen times 14. Does it matter if you do the mass first, then become 14 times 1? It does not. As long as you work out how many atoms you have, multiply by what is the mass of each of the atom. Now you have 3 hydrogen, so you have 3 times 1. Because hydrogen shows as 1 and 1, we use the number at the bottom because there's a relative atomic mass. 14 times 1 is 14, 3 times 1 is 3, 14 plus 3 is 17. Do the same for argon. You can see the argon is just single atom, and from your periodic table, if I'm not mistaken, I actually need to open up my periodic table first. Argon is just 40 there, single atom, yeah. What about carbon monoxide? So CO, there's one carbon and there's one oxygen, so 1 times 12. What I said earlier, I could also do 16 times 1 because as far as I know, there's one oxygen and each oxygen has a mass of 16. So that will give me 28. When you write this kind of thing, it's best to use bracket so you're never ever confused and you can follow your working very well, okay? So what can I say? I can say that the one that goes to the center of the room first must be the lightest. Is the lightest gas, is the lowest mass, or you call it relative molecular mass. Therefore, it diffuses the fastest. If it diffuses the fastest, it will go to the center of the room first, yeah? Number 3, we are talking about the molecules losing speed, all right? Why do you lose speed? So speed is to do with your kinetic energy, and kinetic energy is to do with motion, so you become slower, all right? So as you go from solid to liquid to gas, all right, so going in that order, your particles move faster. In fact, this one is just vibrate about fixed position. This one move randomly at high speed. Okay, so we know very well that vibrating about each fixed position is a very slow motion compared to this moving randomly at high speed. So when we talk about losing speed, it has to be the other way. Maybe I use a different color, then it makes more sense. Therefore, particles move slower going the other way. Whether you go from gas to solid or gas to liquid or liquid to solid, they all lose speed here. They all lose kinetic energy. Lose kinetic energy. So ice to water is actually solid to, if I write on the side, solid to liquid. That one is gain energy, so it's not the answer. Solid to gas, ice to steam, that one is gaining energy, so that one is not losing speed. Steam to ice, gas to solid, that one is losing energy. Remember, gas can go to liquid, gas can go to solid, liquid can go to solid. They are all moving slower, going this way. They all lose kinetic energy. Water to steam is boiling, and boiling require energy, and you will gain in kinetic energy because you move faster and faster until you overcome all the force attraction. Then then you have the boiling point and you become gas. Next bit, guess up until this point, when you see ammonia, you will know the formula is NH3. When you see the hydrogen chloride, the formula is HCl. So this is a very common case study in your diffusion topic in O-level chemistry or any other 14 to 16 years old chemistry that you're doing. So again, we come down to molecular mass of NH3, which is 14 times 1 plus 3 times 1, 14 for each nitrogen, and you have 1 nitrogen, 3 hydrogen, 1 for each mass, for the mass of each hydrogen. And then you compare that with the molecular mass of HCl. So you got 1 hydrogen multiplied by 1, and you got 1 chlorine multiplied by 35.5. These are all obtained from your periodic table. So you can see this is heavier than this. Because this is heavier, it will diffuse slower compared to the 17. So we are looking not at the boiling point, not at the acid or bases, not at the number of atoms, but we are looking at the relative molecular mass, which is what we are doing here, finding the relative molecular mass. Ammonia has a lower relative molecular mass. MR refers to relative molecular mass and not just mass compared to HCl. And in the explanation, the theory paper, you have to show the calculation of the MR for not just one, but both of them to explain your answer because you are comparing. Question 5. Which statement explains why the gases propane and carbon dioxide diffuse at the same rate? So they diffuse at the same rate at the same temperature and pressure. So temperature is one thing that can affect rate of diffusion, but we already know that temperature is the same for both here. So we need to look at the other factor, which is to do with relative molecular masses. So again, very straightforward. You have 3 carbon. Carbon in your periodic table shows as 6 and 12. We are looking at the mass number. So it's 12 times 3 plus 6 hydrogen. 8 hydrogen. So you have 8 hydrogen. Each hydrogen is 1. So there is 36 plus 8 on your calculator give you 44. And the molecular mass of CO2, oxygen, shows at 8 and 16 in your periodic table. So they are all straight from your periodic table. 1 carbon, only 1 carbon, but 2 oxygen. So 1 carbon is 1 times 12 plus 2 oxygen, so there's 2 times 16. 12 plus 32 on your calculator give you 44. And as you could see, they have the same relative molecular mass, and therefore they diffuse at the same rate. Number 6, a drop of liquid bromine is placed in the bottom of a gas jar. So this is a liquid. Brown fumes is a gas. Vapor is a gas. So we are saying that the bromine liquid become bromine gas. You start out with liquid bromine, you put it at the bottom, but then you start getting bromine gas. It slowly spread through the covered gas jar, slowly spread it, okay? So what can we say? What we can say really is to do with diffusion. So yes, the bromine liquid will vaporize. So this is actually it will boil off. Okay, so liquid bromine will boil off. But bromine is one of 2 liquids at room temperature and pressure. So the fact that you are not applying heat means it's not really boiling. So it's actually just evaporation. Okay, it must be evaporation. That some of it must be evaporation because this is at room temperature. You're not heating it. Alright, so some of it must have gone into gas, and the gas particles can move randomly at high speed, and the random motion of the gaseous bromine, the bromine vapor, from a region of high concentration to a region of low concentration. That's the definition of diffusion. So it's definitely got to do with the random motions, and they're always moving. Okay, so it's got nothing to do with density. It's got nothing to do with size, because we are not comparing 2 things. They are both bromine, and they simply spread to fill up the volume of the container through the covered gas jar as well. Number 7, you have 2 containers. One is methane and one is butane. So at this point, you're like, oh, what is methane and what is butane? Do I need to know their formula? Well, read the whole question first. Both gases are released at the same time. The methane gas reaches the flame and catches fire before the butane gas. So what can we say? From this alone, the methane diffuses faster than butane. From that statement alone, we can deduce this fact by using the correct term, diffuses, because diffuses is the verb for diffusion, which is the noun. So methane diffuses faster than butane because methane reached the flame before methane gas diffuse faster. They reach the flame and catch on fire before the butane reaches it. So methane must be smaller molecular mass. So we can say the methane molecular mass must be smaller than the butane molecular mass. That means methane is lighter than butane, and therefore methane diffuses faster than butane. So I'm looking at that. In fact, when they say smaller mass, they refer to smaller relative molecular mass. This is multiple choice, but when you're in a theory paper, you should really use all the proper term, relative molecular mass, all right? Number 8, the slowest rate of diffusion. The slowest rate of diffusion would mean that we are not being told the temperature here, so we can assume temperature is not changing there. So the slowest rate will refer to the heaviest molecule. So we will work out the molecular mass. I'm sure you've seen nitrogen a lot in this paper, or in fact in this topic already. So I'm just showing you what you have in your periodic table, which you can get. Of course, you don't need to write this down in your working, but you know, they're all straight from your periodic table. Yeah, that's why you need to know your periodic table fairly well. So what do I have? 1 so 1 nitrogen, so 1 times 14 plus 3 hydrogen, so 3 times 1, there's 17. mol of CH4, that is just 1 of carbon, so 1 times 12 plus 4 times 1, and it does not matter which way around you have it, it's still going to be how many of the atoms multiplied by what is the mass. The mass number are this number at the bottom, the bigger number of the two. Of course, for this is difficult to tell, but you know, it's given in the periodic table. It's stated that these are the relative atomic number, so that's the mass number. Okay, so 12 plus 4 is 16. mol of O2, that means there are 2 oxygen atoms in one single molecule, so there's 32. mol of N2 is just 2 times 14, so that is 28. We are looking for the heaviest. The heaviest will be this one, therefore is the slowest to diffuse. So oxygen will be the answer here. Question 9, which gas when present? So this kind of question are very common to show the principle of diffusion. Yeah, so this is a porous pot. Porous mean the gases can go in and out. Inside is oxygen, outside, well, this one is just water, outside is air. So if they are equalized, that means the pressure inside is equal to the pressure outside. Yeah? Which gas when present in the beaker? So the beaker is outside here, oxygen is inside. Which gas when present here will cause the water level to rise? If you want the water level at Y, so circle or underline this kind of thing, you want it to rise. What happens means if this goes up, this has to come down because the volume of water here is fixed, right? So if this goes up, this has to come down, has to go down. How can you get the gas inside to go down? Well, this is oxygen. Oxygen exists as diatomic molecule O2. All right, oxygen exists as diatomic molecule O2. So the relative molecular mass of O2 is going to be 16 times 2, which is 32. All right, and then I have to think about the situation. The oxygen can go out because it's porous, but the gas outside can come in as well. If you have to go down, that means the oxygen has to, how do I say this? Let me work out the molecular mass first for all of them, and we'll try and make sense of this in a little bit. Yeah. So of course, I've shown you how to work out the molecular mass of CO2 for some time already. So going back to your periodic table, 12 times 1 plus 16 times 2. The more you do them, you feel like you are getting so used to them. Yeah, I mean, the same concept can come up again and again, and you need to start building your chemistry vocabulary. Chemistry vocabulary meaning the formula of this compound, yeah, as well as recognizing the name. Nitrogen dioxide, so there's NO2, there's 1 nitrogen, and then dioxide because there are 2 oxygen. Pop that into your calculator, there's 32 plus 14, there's 46. So we want this to go down and this to go up. All right, And this question is about diffusion. So I guess you could imagine that obviously I said earlier that oxygen can obviously diffuse out as well, but for this water level to go down and to rise, you need extra number of gaseous particle in here, because at the moment you have a fixed amount of oxygen particle in here, okay, that pushes down on this. But in order for it to push even further down, you need extra number of gaseous particle. And where does the extra number of gaseous particle come in? It has to come in from the outside, that diffuse inside faster than the oxygen can diffuse out. So another way of asking this question is, which gas, if it is here, which gas can diffuse the fastest into this chamber? That means it can add onto the number of gaseous particle in here that it can push further down, because when you have greater number of particles in here, they keep on pushing down on the water level, and they exert pressure, and it will eventually push it down, and this one will go up. Okay, so another way of asking this question really is which gas diffuses fastest into the chamber? Is it chamber they use? I guess you can use the chamber as well. So if this is the chamber, okay, so into the chamber, therefore extra number of gas particles pushing down. So this is really the concept that is being asked here related to diffusion. So the one that is fastest to diffuse will be the lightest one. Therefore the methane gas is the fastest to diffuse in. It will add onto the number of gaseous particles in here, it will push this down, and this will go up. All right. Question 10. The conical flux contains compound X present in solid, liquid, and gaseous state. So there are all three different states of X here. So there's solid X there, and then some of it is in liquid X as well. So some of it must have melted, and then some of them will have evaporated, because you know, melting and boiling only happens at one particular temperature for a pure substance. The fact that you have a little bit of gaseous X is because you close the bunk, so some of the particles on the surface, especially from the liquid, they will have gotten enough energy to escape from the surface and become gaseous X through evaporation. Okay, what can we say? A gaseous X molecule, means one. Okay, so if you have one molecule of X, okay, if you have one molecule of X, does it have a different mass from a molecule of liquid Y as a liquid X? Okay, so if I have 1 gram of H2O solid, it will be the same mass as 1 gram of H2O liquid. It will be the same mass of 1 gram of H2O gas, because you know, this is called conservation of mass. Have you lost any atoms? No, you haven't. The H2O is still H2O. The H2O is still H2O. So you haven't lost anything. You haven't gained anything. How can your mass be changing? Okay, so lower mass is ridiculous. They have the same mass, all right? It is the same mass because it is the same substance, X, X, and X. Energy is released when X changes from liquid to solid. This is very similar to one of the questions that I covered earlier. So going this way, you need energy. So what we say is absorb energy, because you need to break the bond, right? So which means if we go this way, that will release energy, because you know, you're going the opposite way. If this needs energy, this release energy when X changes from liquid to solid. So that is precisely correct. Yeah, liquid X, am I correct? Hang on. Energy is released when X changes from liquid to solid. Liquid X is at a higher temperature than solid X. That is not true, because despite you having more kinetic energy being in the liquid state, but then when you think about it, you know, you are not heating one thing or the other. Okay, they both have the same temperature here, because you know, you have the solid X inside liquid X as well. So eventually the temperature will equilibrate and they will come to the same temperature. Okay, liquid X molecules vibrate. Vibrate is wrong. Liquid molecules slide past each other. and they don't have a fixed position, because although they are closely packed, they have a bit of space in between. This description fit solid, not for liquid. Vibrate above fixed position, that is for solid, okay, not liquid. Question 11. Pure water boils at 100 degrees Celsius. So what happened when the water boils? So this is at the boiling point. What actually happened? At the boiling point, well, you need to think about the heating curve. Okay, so heating curve is the temperature against time. Could be minute, could be seconds, but for simplicity's sake, I'll just leave it as minute. I'll just draw a straight line there, that, and straight line there. This bit here, that is your liquid, sorry, that is your solid going to liquid, and this is your liquid going to gas. That is your boiling there. Okay, so boiling point is a temperature, so you have to label it on the y-axis. So there's the boiling point, and I really should do this a bit better. Okay, yeah, it doesn't matter. Okay, so that would be not that one. Okay, so the other horizontal line refers to the melting point, and we know the melting point of water is actually 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius, only because we're talking about pure water. Yeah, so what actually happened is, at boiling, your temperature is not changing. So as I mentioned in class, your temperature is not changing during boiling. For a pure substance, there is no, it has a fixed boiling and melting point. There is no change in temperature, so you cannot say what am I gonna say here? So it's like the liquids are slowly turning into gas. Not all of them are gas yet. Okay, not all of them are gas yet. So if I look at the movement, they stay close together, is actually going to be incorrect, because here your kinetic energy increase, you move faster and faster. Here you are still gaining energy, but your energy is not being used to make you faster. Your energy is being used to overcome. Energy is being used. Okay, so your temperature is not changing because energy is absorbed or is being gained to break force of attraction between the particle. Okay, so they do gain the energy and they move further apart as a result of it, of you overcoming the forces of attraction between the particle. These are very important in your structured question. Next question, which diagram represents the arrangement of particle in a gas? So we're looking at the gas. So we know that in terms of packing, which is what these simple diagram are showing, they are very far apart. Okay, they are very far apart, which means I can cross out D, and I can cross out C as well, and B is pretty much very closely packed together as well. A is the only one that are like showing them very far apart, which represent a gas better. Okay. Question 13. A sample of a pure compound is heated until it is completely molten and the compound is allowed to cool. So the fact that if you read the question, until it's completely molten, so P must be liquid. Not always you start from gas. Yeah, you read the question, that says it's completely molten, so that has to be liquid. Then you allow it to cool. So this is the cooling curve. That's why the temperature is going down. This must be liquid going to solid. And here you have solid. All right. So I've used abbreviation, but in reality, you should really write out liquid going to solid. And that is your freezing. And we know that this is the freezing point. And freezing point of a substance is equal to the melting point of the substance as well. When are liquids and solid both present? So there has to be Q to R. Very straightforward there. Question 14. Nitrogen dioxide is a dark brown gas. It's more dense than air. Okay, so density is equal to mass over volume. If we say that nitrogen dioxide is more dense than air, So nitrogen dioxide versus air, nitrogen dioxide will sink, air would be on top. Okay, so if nitrogen dioxide is on top here and air is at the bottom, nitrogen dioxide is more dense than air, meaning nitrogen dioxide will occupy the bottom bit. Well, it wants to go down compared to the air due to the difference in density, and air is lighter, air is less dense than nitrogen dioxide, so air wants to move upward. When you remove this glass, this is a brown gas. Remember, if you read the question, dark brown gas. And I hope you know the air that you are breathing in right now is actually colorless. So we need to think about the color. So what is the color inside the gas jar after a long period of time? So this is to do with diffusion. Diffusion is to do with the random motion of particles in all directions from a region of high concentration to a region of low concentration. So this is a region of high NO2 dark brown concentration, and it will move from this region to the region of low concentration. So essentially you will see all of them being brown. Okay, so what can I say? So colorless is going to be incorrect, so C is definitely out. I cannot have a dark brown and a light brown because this would mean that uneven distribution, and this is after a long period. So the gas particle must have moved randomly and occupy the actually, hang on, the nitrogen dioxide is denser than air, right? The nitrogen dioxide is denser than air, so even though it will fill the gas jar, but most of the NO2 nitrogen dioxide would stay at bottom because it is denser than air. So what do we know then? Which means we are expecting more dark brown, but there will be some of them that has enough energy to move around, so we're expecting light brown there. So I was incorrect to say that B and D are uneven distribution, and the uneven distribution has to be like that as a result of your difference in density. So we must be expecting dark brown at the bottom, lower gas jar, that means at the bottom. Upper gas jar, well, there's on top. So bottom will be dark brown and top will be light brown as a result of difference in density. Okay, so I can just write down difference in density, and you can talk about NO2 is more dense than air. Question 15 is this kind of classic question involving diffusion. Typically they ask you ammonia, but here they give you methylamine. Not that it matters because they give you the formula, they even generously give you the relative molecular mass. So again, very similar here, very similar in mass, but this one is heavier. So this one will diffuse faster. If you diffuse faster, you travel at a faster speed. This is it diffuse slower because it is heavier. Diffuse slower because it is heavier. So this will diffuse faster. This one is lighter. Diffuse faster. So A is definitely out. That means this doesn't diffuse very fast. D, C, or B. B is like midpoint. It cannot be midpoint because that would imply that they diffuse at the same rate. That would mean they have the same molecular mass, but they don't. 36.5 is not 31. Okay, and D cannot be D because it's not like so much lighter. If this is ammonia, it will most likely be D because ammonia is 14 plus 3 times 1, which is 17. Ammonia will travel a lot further. But this is 31, this is 36.5. It has got to be this one because very similar, quite similar in the relative molecular mass. Why am I spending time to explain it? Because this can come out in a theory paper as well, and they can ask you explain why. All right. Question 16. An inflated balloon goes down because gas molecules can diffuse through the rubber. We think of it as the gas escaping, but how do they escape? They diffuse. All right, they diffuse out of the balloon. So 4 balloons are filled with different gases, yeah, different gases. Which balloon would go down the quickest? Go down the quickest means the gas diffuses out the fastest. The gas diffuses out the fastest. So again, we need to work out the relative molecular mass. So samol, 12 times 1 plus 16 times 2, so they give you 44. And then CH4 is 12 times 1 plus 4 times 1, they give you 16. And then N2 is just 14 times 2, which is 28. And then oxygen, which is 16 times, oops, sorry, just now was 14. What was I talking about? So if you want it to diffuse out the fastest, we want it to be the lightest. Okay, the lightest. So this is the lightest. Therefore, diffuse out the fastest. So use all the correct terminology. If you diffuse out, that means you escape out, but we use the term diffuse because we are doing proper chemistry, yeah, diffuse out the fastest. So the balloon will go down the quickest. Okay, quickest. So that was it on multiple choice questions. They are not the easiest, but they are not the trickiest of all. Let's get started with this section B question, yeah. Ethanoic acid, not that you need to know what it is yet, alright? But they give you the formula there. And this question is about states of matter. So it's a solid at 16 degrees Celsius. This question is basically asking you arrangement and movement of the particle in a solid. So if I talk about the movement first, solid particles, we know that solid particles vibrate about a fixed position. Well, in fact, it's not just a position, it's vibrate about their fixed positions because we are talking about more than one particle. In terms of the arrangement, they are very tightly packed, very closely and tightly packed. Essentially, what we can be thinking about is the term compact. Okay, very compact packing, yeah. So now the next question is asking you melting point and boiling point. That tell you that you gotta deduce the physical state. Is it solid, liquid, or gas? All right. So to do this, I always like to do my line diagram. If I have my melting point, I melt there, and then I boil there, 118.0 degrees Celsius. What exactly, I don't need to put down the units because I already have the units there. Okay, so where exactly do they want us to do? 130. Where is 130? 130 is roughly there. Okay, give or take. Melting point is when you have solid going to liquid. Boiling point is when liquid goes to gas. Before you melt, you are a solid. After you boil, after the boiling point, you are a gas. So what is everything in between then? Everything in between is liquid. It all comes down to where are you? Well, you are 130 degrees Celsius. It's way above the boiling point, so you must have already turned into a gas. So it is a gas. Okay, so straight to the point. It is a gas at 130.0 degrees Celsius because it already boils, or you say turns from liquid to gas, I guess you can say. Again, it all comes down to how much you want to write, yeah, but the idea is you have to think about the boiling point, yeah, and relate it in your answer because it already boils at 118.0 degrees Celsius. Do I need to talk about the melting point? Not in this context because I'm just referring to the boiling point. If they ask us on liquid, if they ask us on like something like a 17 degree, so there's in between, right? So I have to talk about both the melting point and the boiling point. If they ask us on 15 degree, I just need to talk about melting point. If they ask us on 130, is above the boiling point, I just need to talk about boiling point. If they ask us on somewhere in between, like 100 degrees Celsius, I have to talk about both the melting point and the boiling point, meaning the value is between the melting point and the boiling point, then it will be a liquid, etc., etc., yeah? Question 2. Carbon dioxide is a colorless gas, as you know. When you warm carbon dioxide, solid carbon dioxide changes directly into a gas. So this is sublimation. What is the question asking you? it does not become a liquid. Yeah? Use the kinetic particle theory, you see, kinetic particle theory, movement and arrangement of the particle during this change of state. Be very careful if you read the question. There's solid to gas. So describe the solid first. Yeah. So movement. So what can I say about the movement? Solid particles vibrate about their fixed position. So fairly straightforward there. So the key term is really they cannot move randomly. They only vibrate about their fixed position. Yeah. As it turns into gas, then the gas particles can move randomly. Or in your notes, you can talk about move randomly or move freely, but randomly is probably a better word, at high speed. Okay, so you can talk about freely or randomly, but basically they move randomly at very high speed, unlike this one, only vibration, not at very high speed. Yeah. Maybe I can change color to make you see the contrast with the next point. Yeah, arrangement. Okay, arrangement, the other term for it is packing. So how are they being packed? All right. Solid particles are obviously very close to each other, but that is not good enough because liquid are also close to each other, right? Touching each other. Or you can talk about being compact in a regular manner. So it's very regular and ordered, yeah? Or you can say ordered. All right. Gas particles doesn't have a fixed arrangement at all. Okay. So I don't know what can I say. Gas particles are very far apart. Very far apart. That's all I can say really. So they are indeed very far apart and they are not closely packed at all. Okay. Next question is something similar, but this one is also movement and arrangement of the particles when liquid sulfur dioxide become a gas. So they can ask you different sort of examples. That's how they link to the other chemistry that you will do in the next couple of topics. But the idea here really is using the kinetic particle theory. Talk about movement, talk about arrangement. So, you know, same deal as in the previous question. So it really is like a test of your understanding of what is going on as well. Yeah, so you can put this in your own word as well. So liquids are a bit hard to describe because you need to think about liquid particles. The movement can slide past each other. So we don't talk about vibration. We don't talk about moving at high speed or randomly. Okay, although liquid particles do move randomly compared to solid. Yeah, and then gas particles on the other hand can move randomly at high speed. So meaning to say they move really fast, yeah, in all direction. And the next bit is, again, I should probably use, maybe I'll just stay with blue color. In terms of arrangement, so these are like describe and explain. So it's basically describe, sorry, it's not describe and explain. So you have to specify for both of them, yeah. So we said that liquid particles are closely packed, but have spaces in between compared to solid. So previously we talked about solid being closely packed and compact, but liquids are not compact. Yeah, the liquid particles are not compact. And of course, just to finish it off, you need to talk about the gas particles are very far apart. All right, so they are not close at all. So it's quite funny that you know, this is 2 marks for talking about movement arrangement for 2 of them, but this was 3 marks. So you know, examiners can be a bit stingy or generous depending on your luck, I guess. But if you know what I'm talking about, doesn't matter, whenever, wherever, you still be able to do it. Question 4. So they give you a couple of guesses with formulas and the relative atomic mass being given already. Well, you should know how to get them, right? I mean, straight from your straight from your periodic table, sorry. So which two gases will mix fastest? Okay, so this is a bit weird. I guess this comes down to the lightest, the two lightest, alright? So we are looking at helium and also methane. They have the lowest relative molecular masses out of the list, out of everything in the list, sorry. So which gas will take the least time? The least time, okay? Will take the means one, okay? The least time, so only one gas, okay? Out of these two, which diffuses out the fastest, this is the fastest because it's the lightest of all, alright? So helium will win over CH4 because it's lighter. An unknown gas diffuses faster than nitrogen, so we can say lighter than nitrogen, but more slowly than methane, so we can say heavier than CH4. Where do I get the formula from? Well, you know, you're given the table for a reason, okay? So what can you deduce, all right? So N2, the molecular mass is 28, and 16 is the molecular mass for methane. So 16 is methane from the table, N2 was 28. So what about this thing then? So this unknown gas must be lighter. Sorry, it's about the relative molecular mass, right? So must have relative molecular mass smaller than 28 but bigger than 16, all right? Or you can simply say it has to take a value between 16 and 28, all right? I mean, it's the same thing. What I'm trying to say to you is there are often more than one way of structuring your sentences. Even though you use your own word, it's perfectly fine, but you gotta think about everything you're saying, whether it covers everything that's being asked of you. Number 5 is about change of state, and this is a cooling curve. Alright, so this is of copper, so you melted the copper and the copper cool and then it become a solid, alright? So identify the state or the states, okay? At X is a liquid because you have melted the copper from being a solid to a liquid. And here you have both the solid and liquid copper as the freezing process starts to happen. And here, when no more liquid are present, you just have solid entirely. So here you got a state, you don't need to explain. State what is happening to the energy, there's one, and movement. Okay, so just now we keep on talking about movement and packing, right? Okay, movement and packing. So when you have energy, they are really talking about the kinetic energy. Okay, so your how fast you move and stuff, yeah? During stage X is not freezing. X is still the cooling down of the liquid. It is still a liquid, it is not a solid at all. Okay, so but the temperature is going down, all right, during stage X. So during stage X, the liquid copper, which is a metal, so it's molten, yeah, it was molten, is still cooling down while remaining a liquid. Now I'm gonna explain it, alright, okay? So the temperature drops because temperature is a measure of kinetic energy, right? Okay, liquid particles lose kinetic energy. So we can talk about losing speed as well, yeah? Therefore, lose speed, move slower. Okay, well, actually that is actually part of the 1 and 2 already into 1. Okay, so they lose speed and they move slower. Do I need to explain further? Not really, I guess, because it's stating what happened to the energy, right? I already talked about loss of kinetic energy as the temperature drop. I talk about the movement, so they lose speed, move slower. I also need to talk about move. Are they moving closer together? Sorry, they are not moving closer together because they are still liquid, so not moving closer together. Be very careful, yeah? So you cannot say move closer together. So not moving closer together. Why? Because if you move closer together, then you are having a change of state already, because you are slowly reforming the intermolecular, the forces of attraction between the particles, and you don't want that because you haven't reached the freezing point yet. You're just cooling down. Okay, so one of the common misconception, yeah? Now the next bit is why the temperature stay constant during stage Y. Stage Y is the freezing stage. Why does the temperature stay constant? So as I mentioned earlier, there is no change in temperature. So basically temperature remain constant, right? During freezing. We are not talking about it absorbing energy because this is freezing. So freezing involves releasing energy. Okay, so there's no change in temperature during freezing because there is no change in kinetic energy. Okay, so it's not like your particles suddenly decrease in the amount of kinetic energy. No, not during the freezing stage, because that's the horizontal point, right? Okay, instead at this stage energy is released. Okay, energy is released due to the formation, because this is a cooling curve. So in a heating curve, we are talking about breaking the force attraction between particles. This is a cooling curve, so we are reforming, yeah, formation or reforming of the forces of attraction between the particles such that they move closer together. So this is a change of state during the freezing itself. So it will release energy, but it will not be released as kinetic energy or whatever, because you are not moving slower or anything, because there's no change in your speed, because there's no change in temperature. Question 6 is this kind of analysis of a series of melting and boiling point again. So state with reason which substance could be water. So water is a very specific thing. It's got to be A because of the melting point being 0 degrees Celsius and the boiling point being 100 degrees Celsius. And the reasons are very straightforward. Water, water in solid form being ice. So we know ice melts at 0 degrees Celsius. Okay, and then we also know that water in liquid form, it would boils at 100 degrees Celsius. It boils at the boiling point, it melts at the melting point. How can you tell, or how can you be able to say that all of these substances are liquids at 30 degrees Celsius? So if you think about your line diagram for all of these, where does 30 degrees Celsius come in between? So 30 degrees Celsius will have come in between there, same thing there, same thing there, same thing there, same. 30 degrees Celsius is in between the melting and boiling point of all of these substances, meaning to say if this is where the solid turn into liquid, this is where the liquid turn into gas, 30 degrees Celsius is the value in between the melting and the boiling point for all of these substances. Therefore, all of these must be liquid at 30 degrees Celsius. So all of these substances, oh actually maybe I want to say in between, right? So I'll start off with 30 degrees Celsius is in between the melting and boiling points of each of these substances A to H. Okay, therefore it must be in the liquid state. Which substance remains a liquid over the largest temperature range? So meaning to say, if we have the melting point here, if we have the boiling point there, they're asking us which one has the largest temperature range. So what are we supposed to do is we need to find the difference between the melting point and the boiling point and see which one will give us the largest temperature range. That means the liquid will be existent over the largest temperature range. If you take the differences, between the melting difference between boiling point and the melting point, that will be 100 minus 0, that would be 100. Maybe I should really put down the unit. The difference in temperature still has a unit of degrees Celsius. 65 minus 97. So you need to be very careful of your maths here. Put this in your calculator. You should get 21162. Then 79 minus 114. Again, there is a plus. So there's a 3, 1, 12, 193. 97. So you can do all this on your calculator, of course, and skip to the next bit of the thing there of this tutorial video. 21, 22, and it's not getting any better, is it? All of these are random numbers to me. There's 7, 1, 12, 207. If you spot any mistake in my calculation, let me know. I'm doing all of this manually. So again, there's an addition. So this one is 116, 201. All of these are additions which you should have been able to do back in your primary school, I guess. All right. And last but not least, 195 minus 16. So that is going to be 1, 9, 10, 11, 1, 2, 1, 1. Okay. So which one is the biggest? The biggest range, the biggest difference in the melting and boiling point is that 223. So we're looking at substance D. All right. It's a very straightforward question. It's just asking which substance. So it's not asking you for, explain or whatever. But if you're asked to explain, we'll just need to work out the differences. Okay. This is the last question in this topical test on states of matter involving kinetic particle theory as well as diffusion. So a sealed container contains nitrogen gas. Nitrogen gas exists as this N2, which you would have realized having done a lot of these questions involving diffusion, I hope. All right. So explain why the pressure inside the container increases when the temperature is increased. So you need to use kinetic particle theory or kinetic theory essentially. So the pressure is due to the gas hitting the walls of container. So as temperature increases, what happened to the pressure? Because this is asking you to explain, not just state. So it's very easy to state, right? Temperature increase, pressure decrease, pressure increase, something like that, okay? But you need to explain it. As temperature increase, your gas particles, in this case the nitrogen gas particles, all right, gain kinetic energy. What happens when you gain kinetic energy? You move faster. Okay, you hit the walls of container, more often, or you can say you collide, you hit, or you can use the word collide, collide with the wall, collide with the wall, or you can use the term collide with, or you can use the term hit the wall of container more often. Therefore, since you are hitting the wall more often, pressure will increases. Okay, easy to state, not so easy to explain it in terms of kinetic particle theory. The following apparatus can be used to measure the rate of diffusion of a gas. Explain why nitrogen diffuses faster than chlorine. Nitrogen exists as N2, chlorine exists as CO2, and then that is again N2. So we're just comparing N2 versus CO2. So essentially we are looking at the relative molecular mass of N2. That is 14 times 2, which is 28, versus the relative molecular mass of chlorine, which is 35.5 times 2, which is 71. So N2, or you can say nitrogen, is lighter. Or you can do the reverse argument, chlorine is heavier. Maybe I don't want to use the term lighter, maybe I should use the term relative molecular mass. Yeah, nitrogen has lower relative molecular mass. Try to be exact as possible. Yeah, nitrogen has lower relative molecular mass than chlorine, so diffuses faster. Well, part of my explanation is showing the working, the calculation, and then I can state the difference in the molecular mass. Now the next bit is basically asking you nitrogen versus nitrogen, but at different temperature. At a higher temperature, your rate of diffusion is faster. How much of it diffuse per minute? Rate of diffusion. How much volume diffuse per minute? Okay, so this is higher value, so a lot more gas diffuse at a higher temperature. So this is to do with effect of temperature on the rate of diffusion. At higher temperature, your nitrogen particles, or later on you would use the term molecules, really. Nitrogen particles or molecules. I better spell that properly, just in case for your future references. Okay, they gain more kinetic energy. If they gain more kinetic energy, therefore they can move faster, i.e. meaning diffuse faster. Okay, so it's to do with your kinetic energy. All right, so that's it. That's the end of this topical test, and I hope the tutorial has been useful. And yeah, I mean, in general, this topic is not too bad. Yeah, the question seems repetitive, but I try to show you a range of different kind of questions, as well as different way of the questions that Cambridge like to ask for this particular topic. All right, so thank you for watching, and if you got any questions, feel free to ask me or text me or whatever. Get in touch. All right, thank you for watching.